Hi folks, and welcome to what is in effect the start of year 13, working from the Pure Maths Year 2 textbook. Chapter 1, Algebraic Methods. We're going to start with proof by contradiction. Now you're building up to doing exercise 1a, and as well as proof by contradiction, it makes reference to negation of statements, and hopefully you've read through the stuff from the University of Toronto, which is perhaps a bit more complicated than it would be at A level, but should give you an idea of what negation statements are about. First question, select the statement that is the negation of all multiples of 3 are even. Now to say that's false, we do not need to show that all multiples of 3 are not even. We just need one, and then that wouldn't be true. So B at least one multiple of 3 is odd. If we can say that, we've negated, shown that it's false, the all multiples of 3 are even. We don't need to say all multiples of 3 are odd, because indeed they're not. Some of them would be even numbers if we looked at 2 3s are 6, and that would also do for the bottom one. No multiples of 3 are even, 2 3s are 6 again. So the one that negates all multiples of 3 are even is at least one multiple of 3 is odd. Proof by contradiction. Statement: if n squared is odd, then n is odd. Write down the negation of this statement and prove the original statement by contradiction. Well, this is a badly worded question. There's something missing. Because suppose n squared was 5. N wouldn't be odd. It would be the square root of 5, which is not even a whole number. So this question doesn't make sense unless we preface it with the remark, in this question n is an integer. So I want to write down the negation of, if n squared is odd, then n is odd. And it's the same sort of thing as the one above. There is at least one value of n such that n is even and n squared is odd. If we can just find one where it's not odd, then we've got the negation of the statement. And now we're going to prove the original statement by contradiction. So, if n squared is odd, then n is odd. Well, we'll take it as given then. Given n squared is odd. And I'm trying to prove that then that makes n odd. And I'll do that by assume it isn't. Assume n is even. So I've already decided that n has to be an integer, so if it's not odd it must be even. So if we make this assumption, let's work towards a contradiction, which will mean the assumption was wrong, so n must have been odd. So if n is even, that would imply that I could write n equals 2k for some integer k. But what would that mean? That would mean that n squared is equal to 2k squared. But 2k squared, 2k times 2k, is 4k squared. But now I can take out a common factor of 2. I can say that's 2 times 2k squared. Now the crucial thing here is that the 2k squared is an integer. If k is an integer, and you square it, you get another integer. You multiply it by 2, it's still an integer. So what I've got here is n squared is 2 times an integer, which means that n squared is even. But we were given in the first place that n squared is odd. So contradiction. And if I've got a contradiction, there's only one assumption I made in this problem, and that was assuming n is even. Therefore n is odd, and that completes the proof. Now that was taken from the exercise 1a. Here I've got one that I've made up myself. Let a be a rational number. Let b be an irrational number. And suppose that a plus b equals c. Prove that c is irrational. So in everyday language here, what I'm saying is if you add a rational number to an irrational number, you automatically get another irrational number. So let's set about proving this by contradiction. So A can be written as P over Q, where P and Q are integers. That's what we mean by a rational number, a number that can be written as some integer divided by another integer. B cannot be written in this way. Because that's what separates rational numbers from irrational numbers. Now, I'm saying prove C is irrational. Assume the opposite. Assume C is rational. Therefore, C can be written as, let's say, H over K, for H, K being some integers. But now let's look at this relationship A plus B equals C. So that implies that A, which is P over Q, plus this number B is equal to H over K. And now I'm going to get B on its own. So B would be H over K minus P over Q. But of course a fraction minus a fraction gives you another fraction. So this is equal to, let's put it on a common denominator of KQ. I'll need to multiply the H by Q minus multiply the P by the K, like that. Now the question is that a rational number? Well, it is, because they're all integers, H, K, P and Q, and if you have an integer times an integer minus an integer times an integer, on the top I've got an integer, and on the bottom an integer times an integer is some other integer. But that means that B is written as an integer divided by an integer. So that implies that B is rational. But we started off by saying B isn't rational, so that gives me the contradiction. So if I've got a logical contradiction, what was the assumption I made? The assumption I made was that C is rational. Therefore C is irrational, since assumption is wrong. And that completes the proof. Now then, what you need to do is work right through exercise 1A, one question at a time, then mark it, and I've provided the solutions on the web page. And then finally, there are 2 formal proofs required for the A-level syllabus that could come up on the exam, and I've got little video clips of those for you. You need to learn those, or if you prefer, those proofs are also reproduced on page 3 of the textbook.